My name is Rajeev Nagar, and I am a lead program manager in the Core File Services group at Microsoft. I am joined here by two of my colleagues, Surendra Verma, who is the dev lead for the set of technologies that we'll be discussing today, that we'll be presenting to you, and also by Groff, who's a program manager working in the same group as I, working on the set of technologies that we're going to talk about. By now, all of you must be well familiar with the WinFX namespace diagram that was flashed originally by Jim Olchin in one of the keynotes. I'm not going to talk to you about most of the stuff that's over here. There are other talks that cover the namespaces and the programming model associated with them. But what we're going to focus on over here are a set of technologies that reside in the Windows kernel in the base operating system, and that provide key infrastructure support for two of the namespaces that are highlighted over here, the system.io and the system.transaction namespaces. So those are the ones of interest from the perspective of this talk. From an architectural perspective, well, you've seen this figure before. That's the Longhorn architecture. And lots of modules over here. What we're interested in, what we're going to talk about, are three components that reside in the kernel. Transactional NTFS, we'll talk a little bit more about what that is and how it differs from NTFS as you know it today. And two other infrastructure modules. One is the kernel mode transaction manager, and the other is the Windows log service. These are new components being introduced in Longhorn. So let's talk a little bit about each one of, at least from an overview perspective, about each one of these technologies and what they mean to you. Transactional NTFS, let's start top down. NTFS, since the very early days, since NT35, has been a journaling file system. What that means is it uses write-ahead logging in order to enable fast recovery in the event of a system crash, for example. What NTFS does is it ensures that its metadata is always in a consistent state. And it internally uses the notion of transactions to preserve the consistency of its metadata. However, NTFS to date makes no guarantees with respect to user data. So as far as your data is concerned, you're on your own. And that was by design. Well, what we have done now, beginning with Longhorn, is extended these semantics, where you can now expect to get ACID properties, atomicity, isolation, durability, consistency guarantees for changes made to the file system by you, if those changes were made within the context of a transaction. So that is an evolution of where of NTFS from where it is today to where it is going in the future. You can get these semantics for pretty much all of the file I/O operations that you do today. So if you perform namespace changes, you change file names, for example, you can create or delete file objects within a volume. You can do that within the context of a transaction and get all of these properties that you would expect when you were to do a transactional update. NTFS, transactional NTFS, manages a volume, which is a durable resource, and provides these transactional semantics for operations performed on files and directories within this resource, which is the volume. As you will see later, as Surendra will talk about later, it also manages namespaces at a granularity finer than that of a volume, and allows you to perform transactional updates within that sub-namespace, if you will. Okay, so that's the big change to NTFS going forward. this enables a whole new class of applications where the file system, where you traditionally store unstructured information, data, can now participate equally if you were doing transactional updates to multiple stores where the other stores, for example, databases, supported the notion of transactions. Transactional NTFS relies on and makes use of two new components in the Windows kernel operating system. The new components are the kernel mode transaction manager, KTM, and the Windows log service. So let's talk a little bit about the kernel mode transaction manager. The transaction manager is the module that's responsible for providing the core state engine, provides state transformations when you're modifying, when you're doing updates within the context of a transaction. And the kernel mode transaction manager is a full-featured TM, supports two-phase commit. The big change here is that this transaction manager now resides within the kernel, which leads to tremendous efficiency gains, because you do not, for example, have to do a process context switch when you want to avail of transactional services, when you want to create transactions or manage transactions or commit or rollback transactions. And it's ubiquitous. The kernel mode transaction manager exposes transactions as first-class objects, and so they can be now used either by kernel mode components, kernel mode clients that want to perform transactional operations, or it can be utilized by user mode applications. And you could have resource managers that reside either within the kernel or outside the kernel that can manage resources and participate in transactions that are managed by the kernel mode transaction manager. We will go into more details about the kernel mode transaction manager later in this talk. The Windows log service. So most of us are familiar with the notion of a log service. At least we may have written one in the past. Typically, what you want to do when you're writing, for example, an application that manages a resource, and you want to write state changes to that resource, record them. Maybe you're writing a resource manager. You will need to avail of some form of log service, something that you have developed, some way of recording, persisting these state changes out to non-volatile media, for example. Or you might be writing other kinds of applications, replication applications, for example, where you might want to record state changes made to another resource and then replay them back somewhere else later. Well, typically, what you have to do in such situations is you end up rolling your own log service, if you will, some way of persisting these records out to disk. Well, what we've done in Longhorn is introduced the Windows log service, which provides infrastructure within the kernel to kernel mode clients and user mode clients who want to persist their records. And this is done very, very efficiently. It's done from within the kernel, and it's done in a manner where the I/O cost, which is the bulk of the cost that you incur when you're doing logging, is now amortized potentially across multiple applications, each of whom wants to log or persist their own data. So the key reason for providing modules like the transaction manager and the log service in the kernel are ubiquitous availability, reliability, and tremendous efficiency. The preferred way of interacting or programming to each one of these modules is by using the system.io or the system.transaction namespaces and the methods that are exposed by them. However, each one of these modules over here supports a kernel mode interface, and you can also use for legacy applications as you transition to the WinFX API. You can use those Win32 API in the interim to program to these modules that are over here. So that's the overview of the technologies that we'll be talking about today. Let me hand over now to Surendra Verma, who's going to go into detail on the kernel on transactional NTFS. Surendra.
Thanks, Rajeev. Hi, thanks for coming to this talk. I'm going to talk more about, in more detail, about transactional NTFS here. And let me start off by a demo. Okay, I want to get started, give you a sense of what sort of stuff you can accomplish with this, kind of whet your appetite a little bit, and then go into details. Okay, so here is an example of updating a website. Imagine a web publishing scenario, which I'll show how you can build in a very easy manner by using transactional NTFS. So here's the website, and here is the client's view in a browser to see that site. And what I have here is this shows all the files that constitute that website. Okay. Now the client views the website, and some application updates the site. And let's just say that the application wants to just do this very simply by copying files. All right, very simple scenario. So the application simply goes and publishes a whole bunch of files by copying them into this directory. And let's assume that the application is in the middle of updating the website at this point. While it is doing that, the client goes and hits a F5 refresh. Or what do you see? You see broken links, right? Okay. Well, that's how things are if you just go update files in place. Granted, you could do other things to kind of work around this. But if you wanted to build a simple scenario where you didn't want to play other tricks and you just wanted to do it just straight like this, this is what would happen. What's even worse is that if your application were to just die while doing this, and I'm just going to do that right now. I'm going to kill it. I'm going to kill the window, kill the application, and then see what happens. Well, essentially, your website is partially updated. It's in a broken state, and it's going to remain like that until you can figure out how to fix it. You have to figure out exactly what those changes were that you did and go undo those changes, right? All right. So that's how things are if you were to just use the file system the way it is and try and update your website. All right. Now, I'm going to do the same thing in a transaction. All right. So I'm showing you a different route here, the same website, the same content. I'm going to open it by launching IE and looking at the site. Okay. We're back to the same old site. Now, in this case, I'm going to do this within the update within a transaction. And all I'm doing here is I've written a little app. TXF is a little app. What it does is it starts a transaction with the kernel transaction manager and changes things so that all the commands you type from this point on become part of that transaction. So I'm going to just go ahead and do the same update like I did before, but this time within a transaction. So let's go ahead and try and copy a few files. So stop at the same place. The app is in the middle of copying the files and doing the update. And the client goes ahead and, as usual, does an update, refresh. Well, guess what? The client doesn't see any of the partial changes. Okay? Not only does it not see the partial changes, you may notice that the client doesn't wait for the update to finish. So it's actually seeing concurrently with the updates a consistent view of the website because the transaction is in flight. And that's clearly isolation, right? Okay. So let's just go ahead and say, go ahead, update the whole website. And And let me go ahead and just commit this transaction. Okay? This transaction is gone. We don't need that window anymore. And the client goes and refreshes. All right? So what happened here? This is isolation, right? Transaction committed, the whole new site. So you see the transition from the old website to the new website, nothing partial in the middle. All right? So that's the power of transactions when you push them deep down. You can do simple things like copy and take advantage of them. Okay? So that's one part of the demo. And let me kind of do another trick here for you. So this is another copy of the same website. Let me start a transaction, and this time I'm going to show you rollback. Okay? Remember how I'd killed the non-transactional, the first case, I'd killed the application, and it left the website kind of all messed up. Let's see what happens in this case. So I'll do exactly the same thing. I'm going to copy the same set of files.
Haven't brought up the site.
I'm sorry. Rajeev, what?
Didn't bring up the site.
Oh, okay. I'm sorry. Thanks for pointing that out. So that actually shows another feature here. So Rajeev's right. I forgot to open the site before I started the transaction. Now, clearly, if I were to use that same window and open it, what would happen? I would see the updates, right? Because I'm in the same transaction. So I don't want to do that. So I want to show you the view that the client would see, which would not be in a transaction. So that's why I opened a new window. It's not associated with any transaction. All right? And I can still go ahead and do that. No big deal. Well, I think no big deal. Okay, there you go. You see the old website. And in fact, right here, you've seen that the transaction had already made a few changes, right? And you don't see them. So yeah, the client can come after the transaction started. So that's this case. All right. I don't need this window anymore. So I'm in the middle of this app, the app doing the update. And guess what? The app hits an access violation or something. Or someone just kills it by mistake. Trips on the power cord. Who knows? There are a million ways of killing things, right? Let me just kill it in a very easy manner by just shooting it here. And in all this much time, the client comes and hits refresh again. Well, what happened here? The transaction got rolled back. None of the changes made by the transaction were ever visible, will never be visible, because the transaction rollback took care of all of those partial changes, just undid them for you. All right? So your website is consistent and you're happy. So that's essentially the power of transactions, and I hope you're a little bit motivated now. And I can tell you a little more about the features of Transactional NTFS. And let's just go back and continue with that. Okay. So on with the talk. And this was the demo, by the way. It's website publishing. So here, let's kind of talk about the functionality a little bit. As Rajeev mentioned, this transaction support is essentially very broad. It applies to all file operations that you can do to NTFS. So you can really, a simple way to think about this, it's not really confusing. The simple way to think about this is, imagine the notion of transactions in the abstract sense, right? Don't associate databases or anything else with it, just transactions. Apply that to file system operations, and what do you get? You get this. And you can do this for pretty much any set of operations. You can create a file, you can create a directory tree, populate that, change ACLs on a different file. Okay? Open another file for writing, memory map it, and just change memory. Okay? Go over the network and do a whole bunch of other changes on the other machines, and maybe any number of machines. Take this transaction, go to SQL, insert a bunch of records. Do all of that. And then you have the choice. You can say, oh, okay, I'm happy, I can commit this transaction. I'm in a consistent state, and do that. Of course, it will become durable at that point. The changes will be on the disk. Or you can say, no, I'm not happy, something went wrong. I'd like to just take all that back. I'd like the ACL to be put back, the directory to be somehow unrolled back, the file changes all undone. Everything in the file system should just come right back to where it was. And by the way, nobody has seen these changes while I was working on this, right? So you can just go ahead and roll back. Of course, if the system crashes, when the system boots, comes back up again, It's all taken care of for you. It's rolled back. It's in a consistent state. All right, so that's what transactional NTFS is all about. So we thought of a bunch of usage scenarios for TXF. So this is more like a motivating slide. I'm just going to take you through a few examples, and I'm sure you can come up with many more examples on your own. Because every time we go talk to customers, they come up with things that we can't imagine. This is just broad, really low level. So many different uses for it. Okay, so let's go through them quickly. First one, let's say you have a file and you want to change it. Well, there's no way right now in the system that you can actually change it in a reliable manner and make it work in all sorts of failure scenarios. There isn't. You can open the file, you can write to it. How are you going to change it? If things can crash in many ways in which some of your changes may be there and some may not be there. Of course, you can play tricks. You can copy the file, change it, and then quickly rename it, hoping the system doesn't crash or someone else doesn't come in and try to open the file. You can do those things. And that's what people have been doing. That's just because we haven't provided those. We haven't provided transactions. Okay. With this, all you do is you open your file in a transaction, just change it, and commit the transaction. You're done. Of course, isolation comes for free. Same thing, multi-file update is another extension of the same idea. And it's even more applicable when you have dependencies between these files, links, HTML. We just saw the example like in the demo. Another really popular scenario that comes up a lot is data stored in some database and some of it stored in a file system. And people like to do this for any number of reasons. There are many reasons why people want to do this. And there's a big debate that's going on for I don't know how many decades. That, should we put it in blob? Should we put it in the file system? And again, some of that will probably continue because people have different reasons for doing different things. But there is a large number of people who want to store things in the file system, like in NTFS, and store some information in a database, and would like to see some, the system take care of coordinating changes and consistent backup restores across the two stores, that sort of stuff. And that works. Starting Longhorn. For those of you who've gone to WinFS talks or in some of the keynotes, you might have heard WinFS file stream, file backed items, or references to transactional NTFS. This is what that is. So WinFS essentially builds on top. It exploits transactional NTFS and builds on top and exposes this in various ways, essentially, for new apps, for back compatibility. There are many scenarios, and you'll run into it one way or the other. And some of the semantic changes we are talking about will all apply to you when you use WinFS in some ways. Some of these show through, because that's what they are. So here's a little more concrete example, a little more specific example of a usage scenario. So here, we just got this from a customer and took out all the customer information, obviously, for privacy reasons. But here they have the key data here is mail messages. All right, and this is a financial shop. So these mail messages are really important. Okay, they're protected very well. There's auditing going on. There's compliance requirements, all that stuff. So they come in from Exchange Server, the one on your left. They're pumped through MSM which is a transactional message queue, for those of you know. And from there, the messages are stored as files in NTFS, which is the primary store for them in this case. And some key properties are extracted and stored in a SQL database. Okay? And there is a transaction that pulls stuff from MSMQ and sticks it into SQL, but it doesn't cover NTFS currently because we haven't shipped yet, right? Okay. At the same time, a bunch of other stuff happens here. A client comes in, that's on the right side of your screen, comes from a browser, wants to see mail messages based on certain criteria. Of course, SQL helps with indexing and shows you the messages. And because of compliance requirements, more compliance records are essentially a change history is inserted into the file and the database as well. Okay, just keep track of who's doing what, who's looking at what message and all that. And again, SQL Server, of course, start a transaction, insert the change history. NTFS, no. And this customer is kind of struggling with this right now. They flush NTFS, flush it, make sure it's all on the disk, then they go update the SQL database, and now, of course, they have a very small failure window, right? Well, you got thousands of messages going through this, and you're an enterprise customer, and you got money to throw at this. And you rather like to sleep at night, right? You don't want to worry about, oh, what if this thing crashes? I come back up. Where are all the dangling links? Now, let me write a tool that goes and fixes them up. Okay? So what you really want to do is have a transaction just covers the entire spectrum. Well, the message comes out of MSMQ. In the same transaction, the index information is inserted into SQL Server. The message goes into file system. Transaction is committed. You sleep well at night. The same thing for the browser thing, right? You insert change records. You stick the changes in SQL Server. Do it in the same transaction. It's done. Simple. It's automated. You don't have to worry about it. So that's another very common scenario. Actually, turns out a lot of people do this, run into these sorts of issues. We found. So let's do another demo, which will take you a little bit deeper, kind of look at code, see how easy it is to change file IO code to use transactions. Okay, that's the purpose of the demo. And here we have Visual Studio. It shows essentially a file here, a little program that's dead simple. Okay, ignore all the things are in green. Okay, we'll talk about them later. They commented out. The stuff in black is what the program is going to run. Okay, and I'm going to take this breakpoint off. So all that this program does is creates a file with this name and writes this little thing to it. Simple stuff, right? Closes the handle and it's done. Let's just run it quickly and see how this works. Yeah, build it and run it. Okay. Now, let me go and open up a window so I can actually show you what's going on, right? Okay. All right. So that actually just says this resource manager has already been started, so you can pretty much ignore that. I just wanted to make sure that we had transactions enabled for this resource unit, which I'll talk about later, by the way. All right, so ignore that. And what I've done so far, if you notice, I created the file, and I'm just, I wrote to it and everything else. I closed the handle, and I see the file. Of course I will, right? There is no transaction stuff. There is no isolation. We can even look at the file. It's stuff in it. So that's not so exciting. Sorry. Let's let this just go on. Now the exciting part comes now. So let's just go ahead and make some simple changes, like declare a transaction handle. Just like file handles, event handles, all that stuff, there's a transaction handle. Remember, this is all built inside the kernel and exposed through using Win32. So you got a handle for a transaction, right? Just fits in. So you create your transaction, default parameters. For this demo, they'll be fine. I mean, there are things like isolation level, timeout, that sort of stuff. All right. So create the transaction, get a handle back. Set this handle to the current thread context, okay? And when you do that, the create file, which is unchanged, by the way, you don't have to rewrite your create file. We'll simply absorb this transaction handle, which is hanging off of your thread context, and use it and do the create in the context of that transaction. And also remember that this handle, that is the file handle that results from that create, is transactional from this point on. All right? So that's great. We did that. We don't need this thread context anymore, right? Because this handle is already transacted. So we take that out. So we essentially set it to null, which is the default value, non-transactional. By default, your thread context is null. So when the system comes and you start using NTFS, it's not like you just suddenly get transacted stuff by default. So by default, it'll be null. So the write is unchanged. Set file pointer is unchanged. So the key here is you're not changing your app a whole lot. Essentially, you're bracketing your stuff with transaction code, a little bit of code. That's what we're doing. Close the file handle. Let's just say we go ahead and commit the transaction, and then close the transaction handle. All right? And just to make it interesting, I'll put a breakpoint at commit. So it's going to stop before doing the commit. And we'll execute it and see what happens. Okay. So now, we have created the file, we've written to the file, and we're about to commit. Okay, let's see what's here. So I'm going to hit dir. So here's the question for a t-shirt. What am I going to see? Same? Okay, same. Okay. Another t-shirts. Okay. I think, yeah, this was an easy question. Sorry. We're gonna throw. I know a few people who said same, and that's no file. It's not no file because we had created the file earlier, so it's the same file. Well, I'm being a little arrogant here. I mean, I don't know if I'm going to see that or not. Let me hit dir and make sure. Okay. All right, there. Okay, so this works. You do see it. So this is isolation, right? So the file was there. It had 41 bytes. Guess what? Not only do you see the same file, you see the same length, you see the same timestamp, 527. Let me make sure. Yes, 527. Same timestamp. So you can just go read the file, and it's as if nothing happened to that file. Every little property in that file, every little property is preserved. Every little bit that the file system stores is preserved. And let's just quickly read it and just make sure this works. Yeah, okay. So you see the same file. Let's go ahead, run the program, commit, and just end it. It's not interesting to stop there, really. Now what am I going to see? New file. Someone said new file over there. That's the first I heard, so a t-shirt goes over there. I'm sorry, I want to keep going. Thanks, Dana. I'm going to throw t-shirts when you have a demo. So I heard new file. The first time I heard was there. So it's a new size, same file, new size, new timestamp, 5:30 p.m. as opposed to 5:27. The file has, I can use Notepad, but what the heck? Type just works. All right. So all we had done, we opened the existing file and we appended the same thing again. So there you go. That's isolation. And of course, we saw that in the whole website example. That this is what we were doing. But here you see it in code. How easy it is to just create a transaction, associate with your thread, do a whole bunch of operations that take a name, such as create, and then at some point commit or abort that transaction. And it's a handle. So if you're familiar with handles, this handle just behaves just like any other handle. You can pass it around, you can dupe it, you can do all sorts of stuff. Of course, if you just close the handle, guess what's going to happen? Let's say the transaction is going on and you close all the handles. Guess what will happen? Rollback. Oh, you guys are just too smart. So yes, and that was actually what we showed in the previous demo. I'd killed the window and the transaction had rolled back precisely because of that. I can maybe take questions in the end if that's okay. Okay, thanks. So that's that. And let's just move on and show you one quick thing, and then we'll be done with demos and on with our life. So here, set the delete demo as a starter project. Let me show you what that does. And that's even simpler. All right, that's a dead simple program. I'm going to show you rollback. So it's the same old file that we already have. It's 82 bytes by now, right? I create a transaction. I do the same thing. This time I delete the file. So there is a Win32 API to delete the file. You don't have to open it. It takes a name. Since this is a name-based operation, you got to set your transaction context. All right? Because there is no handle yet. It's the name to handle binding that needs a transaction. And then binding's done. Well, in fact, the delete's done. We set it to null. Let's just run this and see what happens. Okay. So we are waiting for. So we've done the delete. The file's gone, right? God, I thought I'd trick you. Okay. Okay. So the file's not gone. Okay. Not only is the file not gone, you can actually see what it looks like. You can see the file, you can see the timestamp, you can see the date, it's all the same. All right? You can clap, it's okay. It's all right. So here, essentially you've deleted a file, and the file's actually gone. But we just give you this view that you can make out. And this is done all in the file system, so it's not like it's some trickery on the top or anything like that. It doesn't matter how you get at it. It's really there in NTFS itself. Not a layer on top. It's not some sort of funky remapping going on anywhere. Okay? So let's just go ahead, roll back the transaction. What do we see? Exactly. Okay. I think I should just quit now. You guys already know everything. Okay, there. The file's there. Transaction came, it made some changes, it rolled back. This guy, the isolated guy, was completely oblivious to it. He had no clue. Because isolated and then rolled back as well. And so all I had to do was this and this to make my delete transacted. It's not that difficult. All right, let's get on with the talk. And just kind of drill down into a few details. And this might help answer some of the questions that some people were asking, or otherwise we'll take them in the end. So isolation and locking, you've seen enough isolation examples. So the main thing to realize is that the entire file is a unit of locking. Okay? So if a transaction 1 opens the file for any kind of modification, that file is just locked. It's like X locked, if you know locks, row level locks. Okay, this is like a row. X locked, the whole file is X locked. Any other transaction or non-transaction, if it tries to open the same file for any kind of modification, the open is failed. There's no blocking going on here. We don't have blocking locks. We don't have deadlock detection like you would expect in SQL Server, DB2, Oracle, that sort of stuff. We don't do that. And we've got reasons not to do that because we don't have file systems are not like closed systems like databases are. We don't have a full global view of all the locks. So we cannot build a deadlock detector that will actually go resolve your deadlocks and shoot somebody and resolve it. We can't do that because of shares and all that stuff, right? It's a pretty open-ended thing. So we stick with the NT sharing model and NT semantics of sharing violations, and we return a new error code in this case, and you'd know what's going on. Readers don't block, and I think you've seen examples of that as well. We had transactions that were going on, and you could come in, open for any sort of, as long as you open for read-only, and query attributes, any of the reads, you don't have to block, you don't have to wait. You see an isolated view. That's about it. In terms of isolation levels, committed read and serializable. Those of you who are familiar with it. Okay, we can talk afterwards and in more detail if you'd like. Logging modes, this goes a little bit deeper as well and broader. So just to tell you that it's not just a few tricks that you can do, simple commits, updates. No, it's a lot more than that. You can actually set logging modes, and before I go into that, let me kind of explain a little bit. Whenever you're making these changes, we use WinLS to record all our changes, the log to record all the changes, and when rollback is required, we read the log back and know exactly what to undo. Okay, at commit time, we flush the log, or whatever else we do, we'll make things persistent. So this logging modes refers to how much data and what data is actually written to that log. If you're familiar with SQL Server, there are simple and full logging modes are familiar terms. We implement both here and let you select them. So you can do minimal logging with simple logging mode, and for a lot of common scenarios, the data is not actually logged, so it's not as slow as you think it would be. Okay, you create files, add to them, that sort of stuff, or even delete files. The data itself is not logged because in many cases there is no before image to log, right? In full mode, of course, we log everything. So it costs more. If you write 20 bytes, it will be written to the log as well. But guess what? It's a full history of your transactional changes stored in the log. Okay? And we'll get to why that's useful in a minute. This is part of it. So imagine an example where you have an app that's not like a vanilla app that's updating a little Word document. You have a whole collection of files that's very important to you and for which you really want to control how transactional operations happen to those files. And these are just your files. For example, you may say, oh, for these files, I would like all the logging for it to happen in just that log. And that log should not take anybody else's log record. It's my private log just for those files. Okay? Imagine database, a little database. This is not a database, by the way. But it's like a little instance for transactional processing. You may set the logging modes based on your needs. And you may set log policies, growth policies for the log, and all that stuff. Now, the scenario that you can easily build and imagine is the one in which you've set this up as private log for your files, and you're pretty good about doing backups every week, every night, whatever. And you also back up the log on a continuous basis. And you will see how that works later in the WinLS part. And now you've got essentially a continuous backup solution, which applies to all the transactional work only, by the way. And then at a later point in time, you can just restore just those files, not the whole volume, not the whole system, just those files from the backup. And you call some APIs to make sure you pick up all the stuff that we maintain. And you restore your files, you restore your log, okay? And you call a whole bunch of APIs and say, all right, I'd like to roll forward through this log to that point in time. You can do that with file system, with NTFS in Longhorn. Okay, so NTFS will essentially read those logs and redo those operations that are in the log and take your file system state forward just for those files, not for the whole system. And the way you do that is through a resource unit. In fact, all the examples I was showing you were all individual resource units. And the one I had done the start with, there was an error. I was just starting a resource unit. So you can start and stop resource units via APIs. And that is essentially your unit of your private app private data, essentially. And you can move the unit as a whole. You can start and stop it. Put the log anywhere, on any other volume, by the way, for efficiency, reliability reasons. And just so you don't get the wrong idea, you don't have to do all this to use transactional NTFS, because this is pretty heavy stuff. Very powerful, very heavy. Bunch of APIs that are arcane. If you know what these are, great. You can really build a powerful solution. But you don't have to do that. You can just start a transaction and start working on any file, anywhere, in any NTFS in Longhorn. You don't have to start transactions or create resource units. Because the system comes with resource units. In fact, every volume has a resource unit that's built in. And it automatically covers all the files that are not in any other resource unit. So it's like the catch-all. Okay? And that resource unit is self-managed. So you don't have to worry about where its log is, how does it grow, when does it grow, how does it shrink, when does it shrink, when does it recover. You don't have to worry about all that. You do your work, the system crashes, it comes back up. We will know how to make it consistent. We will just recover automatically when the system comes up and the volume is mounted, essentially. The log will just grow as needed. It will shrink when it's not needed. That's simple. It will just work. So that's your system managed resource unit. And just kind of like in conclusion, how do you program to it? Well, I've shown you a programming example using Win32 essentially. And you can also use system.io, system.transaction combination to do similar things. System.transaction layers on top of KTM, Win32 APIs I showed you, the create transaction API, system.transaction layers directly on top. So you go through system.transaction and it maps down very fast to this one. At the same time, you can take that the managed transaction object, use that with the system.io APIs, WinFX APIs. Okay, and all that is coming in Longhorn. So the bits that are given out in PDC don't have the system.io and system.transaction mappings. But at this point, what is out there has Win32 support, and you can just use that. All right? And we have hands-on labs, and we have pointers to that at the end. I would encourage you to go try out some of these kinds of examples if you would like to, and ask us questions. Okay? Thanks for listening to this part, and I'm going to hand over to Rajeev, and he's going to continue with the KTM, more details and more drill down into the transaction manager. Okay, thanks.
Thanks, Surendra. So Let's talk a little bit more about the kernel mode transaction manager, what services it provides, and how you can leverage it within your applications. So this is base kernel infrastructure for transaction support. As I mentioned before in the overview, the kernel mode transaction manager services both user mode and kernel mode clients. It doesn't matter where your application or your component resides, you can avail of the services provided by the KTM. The KTM, again, by virtue of the fact that it resides in the kernel, you don't have to do any kind of process, context switches to go to some other process context in order to avail of its services. So it scales well, it's very efficient, and it's available to all kinds of clients. And the kernel mode transaction manager is very well integrated with the DTC component. For those of you who've done DTC-based, who've written OLATX-based applications before, and have used distributed transactions, for example, the kernel mode transaction manager supplies the state machine core for distributed transactions and integrates with the DTC, and then you can avail of all of the protocols that DTC supplies you with in order to distribute your transactions across different machines. So let's just see a distributed transaction flow. How would you avail of the services of the KTM, both locally, and then how do you go across different machines? So let's say you've written an app, resides in user mode. The app decides to do some transactional, perform some instructions or execute some operations that are transactional within the context of a transaction. It uses the WinFX API, and the app decides to create a transaction. Well, if the app is going to use any kind of durable resource, for example, a file system, then that transaction, WinFX, basically system.transaction, will propagate this directly to the kernel mode transaction manager, which is now managing that transaction effectively. And the app then decides to do some sort of I/O, file I/O. So it just decides it's created a transaction. It's, as Surendra illustrated in one of those examples, it's then bound to that transaction in some way, shape, or form. Using WinFX, for example, that's the ambient transaction in whose context you're executing these operations. And then you decide to do some file I/O. Well, as soon as you decide to do some file I/O and that call reaches NTFS, the operation is now being serviced by NTFS. NTFS recognizes that you're doing some transactional operation and therefore enlists in that transaction seamlessly under the covers with the KTM. So this is seamless to you, to the app that's performing the transactional update. The enlistment happens under the covers, and NTFS is now a resource manager. Transactional NTFS is a resource manager managing that resource, which may be a volume or a RU that is within a volume at a finer granularity. So now the app continues doing its I/O, and the app decides, I want to distribute the transaction. I want to take this transaction and send it to some other machine out there on the network. Well, the app's going to do that by invoking a marshal operation via the WinFX API again. And so the app invokes this marshal operation, and the transaction is marshaled, a blob is constructed, and the app uses some mechanism to transmit that blob across the wire to a peer app residing, executing on some other machine out there in the network. So this is a blob, contains all of the information about the transaction, sent in some manner across the wire to my peer app somewhere out there on some other machine. Well, that peer app that's executing on the other machine says, I've received the blob, I want to do something with it within the context of this transaction. And so it calls an unmarshal. It invokes the unmarshal method, uses WinFX for that. Well, by virtue of the fact that it does this unmarshal operation, communications channel is established across these two machines. Communication resource managers on both machines get involved automatically. KTM instances on both machines are now aware that there's a transaction being unmarshaled. There's this channel that's been set up across these two machines. And the unmarshal operation completes. This is all under the covers. All that the app has done is executed this unmarshal call. And the app now, which is on this other machine, decides to do some sort of update to another transactional store, for example, to SQL Server. And that transactional update can occur now within the context of this distributed transaction. again seamlessly. So you now have a transaction, a distributed transaction, spanning two different types of stores. Transactional NTFS on one machine, SQL Server on two different machines. And then the transaction can naturally either be committed or rolled back. And the right thing will happen on both of these machines on each one of these stores. So it's very easy. It's very easy to use KTM and avail of these transactional services in your application, whether you're doing just local updates or updates across the wire transaction within the same transaction context as a distributed transaction. Now let's imagine that this app, let's imagine that you didn't want to do any update to SQL Server. Let's imagine that all you wanted to do was create a transaction and you were doing I/O to NTFS, to the file system, transactional NTFS. So as Surendra illustrated, all of those operations, those changes to the file system are executing within the context of that transaction. Well, let's assume that your app decided to do some updates or changes to a volume, to a network share, to a volume that resides on a remote file system or on some server out there. Well, in that situation, effectively, the reader and the server components that are within the kernel that use the SMB protocol in order to take your file I/O operations and transmit them across the wire will do all of this. The marshalling, the unmarshalling will be done on behalf of your application by the reader and the server executing on these two different machines. And the KTM instances on each one of these machines will again be involved seamlessly under the covers. The communication resource managers will be involved seamlessly under the covers. DTC will be involved if you're using DTC will be involved in order to coordinate this transaction potentially. And you could extend this model, by the way. You could do operations to your local file system, to a remote share, and to SQL Server on a remote machine. And essentially the same logical sequence of operations will happen on your behalf. So all of this infrastructure exists. It's there in the kernel. It's provided for you, and you can write applications very simply that can utilize all of that. Oh, by the way, instead of SQL Server, you could have any other transactional store that, for example, uses XA, that can interface with DTC, and it can participate in these distributed transactions. So this should give you a sense of how you can use transactions both locally and remotely on file systems and on other stores. I was supposed to go forward, not back. KTM, again, is a full-featured transaction manager. It implements two-phase commit. It implements this notion of virtual clocks that allows for temporal ordering across multiple RMs or resource managers. KTM also provides functionality like save points, so you can do intra-transaction rollbacks. So if you do not want to roll back the complete transaction, but roll back to a point in time within the transaction, you can do that by using save points. It supports roll forward recovery. So for example, Surendra spoke about roll forward recovery that Transactional NTFS, which is a resource manager, supports. Well, you could do roll forward recovery with KTM and its log, and with TXF and its log, so you can move forward to a point in time. You can roll forward to a point in time to where you want to go. KTM supports multiple logs. In a clustered environment, you could do log failover. If the log is one of those components that's part of a package that's failed over in a cluster. It's well integrated with the various protocol layers supported by DTC, for example. And KTM supports kernel APIs interfaces. It supports Win32 interfaces for your applications as you transition to the system.transaction interfaces or the managed interfaces. So that's more detail about the kernel mode transaction manager. I'd like to call Dana now, who will talk a little bit more about Windows Log Service.
Thank you, Rajeev. So the Windows logging service is a tool that both the KTM and Transactional NTFS use to remember their state, to be able to save off what they've changed. What are they doing? They're saving sequentially record-oriented data. Okay, these are a batch of records. They're stored in a sequential time-arranged way. You group them. So you have a transaction, but you've got a lot of different changes. If you want to roll back that one transaction, you want to be able just to look at the records involved in that transaction. Logs write I/O. They're persistent. You want them to have a great deal, incredible high performance. You don't want the log to be a hot spot. You don't want the log to sit there and have a performance impact at all. So the Windows logging service is optimized to be able to provide you the sequential record-oriented data to write it out and, in fact, to share IOs across multiple different users. So an example of some of the things that use this are transactional stores. Maybe you want to save a batch of records so you can replicate the data across multiple machines. You take a backup of an NTFS thing, you use a full logging scenario, and then you use that log to replicate the data. That's a Windows LS log. You might be doing fairly simple logging, event logging, security logging. These aren't doing transactional things, but you want that data. You want it together, and you don't really want to deal with the hassles of checking to see, in a case of a multi-sector write, did you actually complete that when a system failed? Windows logging service deals with an atomic multi-sector write. It will do it for you. So let's do an example, a data flow example here. This is the overhead, and we're going to get into code in a second. So I have two applications here. They could be two different processes. They could be two different threads within one process. They're writing data out. They're saving that in the log. And they do each of those records, and they puts them into a buffer. We call it a Marshall buffer. And when you actually append into your Marshall buffer, we assign a unique log sequence number, and we call it an LSN. It's a unique number that identifies this record. We encode that as you're writing those in there. And what you're doing here is you're batching these updates so that when you flush your data, there's only one kernel transition. Once you flush that data into the WinLS flush queues, notice here I've got both applications flushing that data into the same flush queue, and then they can batch their writes into one I/O out to the disk. So you're sharing an I/O. This could be 2 applications. This could be 5 applications. This could be 10 applications. It's not limited there. Think about an environment where you've got a transactional system across multiple processes, and they're all writing to the same log. One I/O. They've got, especially in the case of multiple RMs, they're sitting there going, I've got to remember all these states. I've got, maybe in a case of database, I'm writing a batch of things into my records or the file systems. I'm writing a batch of things into my file systems. I don't want to have 2 I/Os for everything I do. I don't have to do that. I can share my I/Os across multiple different other applications, other RMs, by all of us sharing a log. So let's take a look at the code. And I'm going to actually walk you through what we just saw in that nice, pretty picture, and do it in code. In fact, it's easier to do it in code than to come up with that pretty picture. Okay? So, how many people here have actually looked at our log, at our labs, HOL, Hands-on Lab 404? Okay, you get a shirt. In fact, everything you've seen tonight is in those labs. So you can do those labs. Got another one? Well, great. You can do those labs, and you can see all these demos. They're right there. And of course, this is on ComNet. These demos are also in a zip file on ComNet. So these are real bits, much to our sometimes worry. These are actual real bits. This is the PDC disk you have. This is, this you can do. So anyway, so it's out there. And forgive me if anything goes wrong, because this is real bits. And I don't want the class view. Give me a solution view. Thank you. So I'm pulling up TXF here. I'm not Don Box. I don't write code interactively. And this is a little more verbose code. What I'm going to do here is I'm going to set a breakpoint at all of our stuff. And
Example.
watch this.
It's a wrong example.
Did I get the wrong example? This is the TXF. Oh, I got the wrong example. That's why. Thank you. I've been looking at this code. It all looks the same after a while, doesn't it? So here we are, and I'll do a quick reminder. We wrote a batch of things into a log file. So this is going in the nice, pretty picture. The file seemed to already be there, but in this case, we don't have a file. We have to create that file. So I'm just going to hit F5 here, and we're going to build and start. So we're here at create log file. Now, what I have in creating a log file is a log name, and that is a full pointer right to there. We haven't put an extension. It's the extension will be BLF or base log file. Pretty standard file things. Open always. I'm going to actually create it this time. So we'll step forward. If you actually want to see that, that's all right. I'm doing it. See, there's our log BLF. So now I'm adding a log container set. I hadn't talked about containers, but it's not a single log file. It's a log which is made up of multiple files, which we call containers. Each of those are the same size. They can go anywhere. NTFS, FAT, on an SMB share, that's fine. You can put them anywhere. You can put them across multiple disks. This allows you a lot of flexibility in managing it. You want to expand your log, you add another container. You want to shrink it, you take some containers away. Right here, we're just getting a full path name for those logs. And in this case, I'm using the add log container set for doing multiple at one time. So again, we'll create that. Now we're creating a log marshal area. That's that buffer. So we're creating this buffer. You can make that a large buffer, stick a lot of things in it. And here is what we call reserve and append. Now this is allowing us to atomically reserve space and append things. We're putting it into that buffer area. But we've guaranteed that we have space on the disk if this command succeeds. Now, mind you, best practices here is you do check to see if there's a success. Okay? But I'm trying in examples of demo to make it clear and not write that much. Flush the log buffer. This is going across the kernel transition boundary. Now, in this example, what it would have been easier is if I had used this flag to force the flush. So I could have actually said for every time I reserve and append the log that I actually force the flush. Or I can wait and control it myself. And then I simply clean up. Now,
so have you guys taken over the cache manager functionality then? Or are you using the cache manager?
We're using the cache manager. I mean, honestly, we're all in the core file systems. But let's talk about those a little bit later. Surendra, where'd you put my stuff? I think you may have closed my window. Yeah. Yeah, but I think you closed my window. Anyway, so one of the things that I have out there, live bits, folks, really. There we go. So one of the things that I have out there is in the labs you create what they call an LS control. And I wanted to show you here that, in fact, we did write something to the log. The 1 fish, 2 fish, red fish, blue fish. I think some people might recognize that. And I've dumped some information out about how those logs are created. So that's a quick first demo. Let's get to the next level. I've been talking about sharing IOs. How do I do that and yet still keep applications from breaking? I think it would be a little confusing if, as I read back those records, I see somebody else's record. In fact, I might really not want, as an application designer, to have somebody else see my records and potentially, modify or get rid of them, right? I wouldn't want that. So I want to be able to write my records into the log in kind of an isolated way. We do that through log streams. Think of this as a way to really parallelize writing into the log. Inside the log, they're actually interleaved. But you don't know that. You can't see that. As far as the user is concerned, each stream is just their log. Now, the really neat thing about using streams is it doesn't change your code. All you have to do is put : stream name. Everything else is the same. So all that code you saw before, add : stream name. And it's simple. The advantage of doing that is I now can share that. I can have a stream for one app and a stream for another app, and we're all going to share those IOs. And I can isolate them. I can set ACLs on these streams. All sorts of cool stuff. No problem. Let's do that. Nice, simple, fairly easy thing to do. So here we are. This is my Don imitation. I have my stream 1. Now I will note that I renamed the log because the first time I created it as something called a dedicated log. So I've changed that a little bit. So here we are going to be adding those containers, new containers, because this is a different log. It would be kind of bad to share containers. And also would give an error. That would not be good. Everything else is the same. So that's my change. We're done. So let's compile that, run that. Okay, there we go. I'm just going through this. You've all seen it before. Go back here. Yes, they do exist. And, in fact, where's my little command? Here we go. So here, I'm just going to, again, say that in stream 1. That's there. Yeah. Live. Oh, I need another colon. That's right. That's bad. There we go. So there it is. Now, what's this?
We check for errors.
We check for errors. Right. So, hey, but what about another stream? So here I'm going to just do a second stream. I'm going to note that I'm going to just comment this out right here. We don't need to add any more containers. And just so you know, when one from the other, it's going to be 2 fish, 1 fish. Sorry, Dr. Seuss. I think that's all I need to do. La-di-da-di-da. We walk right through it. Are we done? I think we're done. Oh, we started again. Okay, but that's good enough. Do the same thing. Let's take a look at stream 2. 2 fish, 1 fish. And if we prove to me that I only see it again, one fish, two fish. You can do them in parallel. I would need more. I need to be cleverer on the demo in order to do that. So please excuse the lameness of that. It was easy to write. Okay, now I've been writing a lot of things. After a while, I'm going to fill those containers up. Probably not with just one fish, two fish, and a couple of different editions. But let's say I have real data and I have a lot of it. I might be doing full logging, other things like that. So let's say I'm doing full logging. I'm going to want to remember that, especially before I recycle the space. I can remember it. Stuff can still be there. That's fine. I can archive that. And you know, when I'm archiving that, the API we provide you doesn't block people from reading the log, people from writing to the log. The archival stuff happens without blocking any activity to the log. And that's fairly interesting for those people who've worked with databases over the years. You know, you sometimes realize, oh my God, I've got to back up a couple of terabytes, and it literally can stop users. Not here. Now here's something that I haven't introduced before. It's called a restart area. And you may have noticed that the animation also got rid of some of that orange. So what I just did there is I wrote a restart area, and I recycled some of my log. Now, a restart area is a shortcut. It's a tool we provide you as the user primarily of an RM. So an RM is calling the logging system, and he wants to be able to return to a state in time, a consistent state in time, and start reading his log forward. So what he's doing there is saying, hey, I know at this moment where I am and what's in my log, and I can forget some data. I don't need it anymore. For instance, somebody has committed and all that stuff to roll back. I don't need it anymore. So I can just say, forget that data. Now I'll put it into a restart area. You can put anything you want in a restart area. Probably a common usage there is you're going to stick a batch of pointers into your log, saying, look here and look here. This is the beginning, whatever. But the neat thing about a restart area is when you come up because something happened, you can say, show me my last restart area. And that's also how you forget things. We give you a shortcut for those people who are doing full logging, who are writing archives out there, to keep what we call tail and your archive at the same point. There's no need to do that, but it's just a shortcut. So again, how do we do that? So here we are, TXF, delete. No, that's wrong. That's TXF. Restart. Ah, yes. So we do that. Okay, so I'm still debugging. Let's stop. And set that as a startup. Here's the code. I've already set the breakpoints. It should look familiar. We've got create on a log file, so we're just opening up. This is a new call. It's to get log information. It's telling me information like where a restart area is, what the beginning of the log is, what the end of the log is. I'm using it to get my last record. And then I write a restart area. The restart area really has nothing in it for this example. And then I clean up. We're doing this on the log that we created at the first example, which does have at least one record in it at this point. And if we run this, at this point, once we've written a restart area, this is now empty. Go back here, and I'll just finish that out. That's how you do it. Very simple code. All of you who write file systems know how to do this. It's just pretty straightforward. And that's one of the things I want you to remember. This is easy. This is easy to do. In Win32 even. Okay? You can't, there's some managed code which is not available in the PDC bits, but you will be getting something in a WinFX that actually allows you to work directly with the Windows logging service. Win32 is there now. The kernel is there now. Real easy to use multiple streams. We really provide some nice things to do logging. And in fact, for those people who are database people, and you can talk to me later, we talk about Aries logging. Yeah, we support Aries logging in Windows logging services. You don't have to do this. You don't have to worry about atomic writes and torn write detection. You can just use Windows logging service. It just works. It's pretty cool. So that's the end of our talk today. Rajeev?
So we want to hear from you. We have some labs over here. We highly encourage you to go to those labs. Please try out all of the examples. Many of the stuff that you've seen over here, much of it is present over there in the form of labs that you can execute yourself. Play with it. Give us your feedback. We will be available to talk to you Thursday, tomorrow, 9 to 11. We're happy to talk to you. Would very much like to get your feedback. Please feel free to send us email if you have comments, suggestions. And then 309 Foyer, yes, we are there. There are other speakers there from PDC 2003. There's a news group. So various ways that you can interact with us. And if you have any questions, we'd love to answer them at this time.
So I should add that in tomorrow and even now, the developers directly working on KTM and Log, John and Dexter are actually here as well. They'll be also there. You can ask them more detailed questions and things like that. Okay, questions?
Transactional log itself, is it transactional? When I create it under transaction.
Transactional log itself?
So you're talking about in Windows logging service. Now think about what you're asking. Do you want me to actually have a transaction around writing information I'm going to use in the transaction? So the answer is actually, I believe, no, if I understand your question.
Yes, but from other side, I may participate in the existing transaction. So I have transaction which I write to the database to the file which already have the file log, right?
Okay, I'm not understanding your question. So
log for the file system itself, for the regular file system, it's always present, right?
The regular file system, yes, it's always there, and it's suppose your file I/O calls. Please continue.
Yeah, and then I create another log for something different which I'm going to do under this transaction.
Yes.
And then transaction roll back. What happened with the log?
What other work are you talking about? So
This log which I create under this transaction.
So we don't allow creation of these logs under transactions themselves. So these logs are actually designed so that you can build a transaction store using the logs. So if you're a transactional resource, you would use the log. You wouldn't create the log in a transaction. You would just, if you wanted to create files, if that's all you wanted to do, you could do that in a transaction, but not the logs themselves.
So the create log, you're creating a log file, which is different than creating a file. And so that's not a transacted operation.
Okay. Question?
So if I want to use a log to trace as tracing log or event log, talking a mic.
oh yes,
Okay.
the mics, correct.
Mic.
There are mics here and there, so that's all right.
Actually, sorry, I can repeat your question and then we can go there. Sorry. Go ahead. I'll repeat your question.
So my question is, if I create a log to trace my steps, and this is part of transaction, can I do this as part of transaction? So log basically will say transaction failed or transaction, doing step 1, doing step 2.
Okay.
Can I do it inside of transaction?
Can I repeat the question? The
Please
question
do.
is, here I've created a log and I'm writing these steps, which are sort of have transactional flavor. So, and then I would like, when the transaction to abort, I would like those operations to automatically be undone, if you will. So essentially, your updates to the log themselves, you would like those to be transactional.
No, my question is, how will it behave? Because I thought you just said that I cannot use logging API under transaction.
Okay, I see the confusion. So the log itself is created under the covers, and then you have to write a whole bunch of code on top to read the log and then implement transaction semantics. So it's not like you create the log itself in the transaction, if you know what I mean.
The log does not participate. The log does not participate as part of the transaction. Log
Right.
does not participate as part of the transaction.
Can I answer
That's
that?
what I think the answer
Let me
is.
try and restate your question. I think what you're saying, and please correct me if I'm wrong, is I create a transaction, I'm doing some operations within the context of that transaction. I want to record the fact as to whether the transaction succeeded or failed, so I'm doing some logging along with this. Is that correct? Okay. So now whether that transaction succeeded or rolled back, I want to continue to log and perhaps then consume the log to find out what happened, right? And you could indeed do that. So what you're doing for that is you're going to create your transaction. Underneath the covers, some log is going to be used. You're not concerned with that log, okay? You're going to do some file I/O operations, which are transacted operations. So you can abort, you can roll back or commit that transaction. Now, you can create your own log. You can use Windows logging service. You can create your own log file, and you can record whatever you want to record to that log file. That is not part of this transaction, okay? So you can record that my transaction rolled back, my transaction committed, and whatever happens, this persists, okay? So this is just a mechanism that you can use. Now, internally, just to clarify, internally, the kernel mode transaction manager and transactional NTFS also have logs that they use, which you do not deal with, you're not concerned with. Okay?
Different logs.
All right.
So we have another question over here.
Yeah. When you basically,
Speak closer.
Yeah. Hello. Yeah. When you basically update a log with a private log, which you want to maintain, should it be out of the process? Should it be in the same? Can it be in the same process, or it has to be a different thread, which basically it's not required?
Yeah, it can be in any thread or process.
Okay.
The transactional stuff that happens only when you bind the transaction to the thread. So you would be binding it and then unbinding it when you're done with the file I/O operation, which is transacted. And then when you do your log operations, your thread is not bound to any transaction.
Okay.
And therefore, you can then do the log operations, which are not in the transaction.
So the second question I had is, for example, when you do a backup and restore, right? You restore just the file, but not the log file. Okay. Will the roll forward happen in such a fashion that it will go to the point of failure rather than point of time?
Okay, the question I don't need to repeat, but so this question refers to the resource units and the advanced options, right? In that case, the backup and restore are initiated by the app, by you. And you would be responsible for backing up and restoring the files as well as the log. And then once you restore both the files and the log, then you call APIs, TXF APIs to then essentially say, please roll forward to this particular point in time.
Yeah, I might not want to test the log file at all. I'll just leave the log file as it is from the crash, and I'll just restore the file which I have backed up and use the existing log to roll forward so that it comes to the
that might work in some cases, yes.
That might work, right?
That might work, yes.
Okay. For example, if I want to back up the log volume, again, the VSS infrastructure should be okay as long with the open handles and things like that, right?
Yep.
Absolutely.
Cool.
Yep.
Thanks.
Yep.
There's, by the way, 2 mics for if anybody over here wants. There's one over there as well.
My question is, what happens with kernel mode file system drivers that sits under just above NTFS? If the change goes down the file system stack, I see the change, and if I ignore to send it down and just not send an ACK back, will that transaction fail?
So you're talking about kernel mode file system filter drivers.
Correct.
And what I would highly encourage you to do is to develop to the new filter manager architecture that we are rolling out, that you should now be familiar with, which provides infrastructure for you that allows you to understand whether some operations are occurring within the context of a transaction. You can potentially, if you so choose, decide to influence whether that transaction succeeds or fails or not. That's up to you, okay? Right. And then you can do the right thing because now you know exactly what's happening and when the commit operation occurs or when a rollback occurs, okay? So my advice over there, again, so we recognize that there are these kernel mode filter drivers that need to understand exactly what's happening in the system. We have provided infrastructure support for you and you can leverage that infrastructure support that's there in the new filter manager with the filter manager architecture. And as long as you port to that and then and leverage that infrastructure, you should be okay.
All right. One other question. When you do full logging and you keep history of that log, is there a way for us to actually inspect that log to see what the changes were that happened, and does it carry any kind of delta about the change, or is it just the fact that there was a change and this is the type of change?
So you're talking about the transactional NTFS writing log records, and this is full logging, and you would like to, what you're asking is if there is a way in which you can inspect if there were changes, etc.,
Right.
what the changes were. There are APIs to read log records as well, and we're still working out. We'd like to kind of talk to you maybe offline about your requirements and in terms of what you would like to get out of the log. I think we do envision some sort of support there for getting some sense of what's in it.
Yeah, it'd be interesting to know exactly what you want from it.
Right.
For example, the USN journal, for example, is a different mechanism for you to find out exactly what happened.
Right.
And that might be sufficient. So it'd be interesting to know exactly what you intend to do with that log, with the internal NTFS,
Right.
transactional NTFS log.
Okay. Thanks.
Does the KTM offer any sort of native support for long-running transactions rather than pure DTC ones?
No, it doesn't.
No.
Sorry.
Shame.
Question about transactional NTFS. When you delete a file as part of a transaction, if you then go and open that directory and were to read through it, the name should not appear if you're in the context of that transaction. Correct?
Yes.
Correct.
But other people will continue to see that.
Correct.
Yes.
And they can read the file. They cannot open it for writing.
But within your world, it's gone, and you
From-
never see it.
Within the world of the transaction, so there are two worlds here. The transactions, the world of the transaction that is doing the work, the file's gone. Right. Should get that picture.
I have a question related to how do we know that a particular log generated with full logging mode can be applied over a restored backup?
So the question is, how
So-
would you know? Okay.
Yeah, how do we know that this log can be applied over a full copy sitting on my disk?
Okay, we should probably take this offline. It's a little bit detailed. Basically, we don't envision at this point any sort of catalog support, if that's what you're talking about, cataloging when I backed up which log and how does it relate, etc.
Yeah.
We don't envision providing that support, but we can talk about that separately.
Okay,
We
and
expect you to kind of just keep track of that at this point.
does writer block the another writer, or?
A writer in one transaction would block another writer in a different transaction or non-transaction, but you can have many writers within the same transaction, of course.
So you mean a writer is going to be blocked even if it is out of transaction in any other process, right?
Right. So yes,
And
once there is a writer present for a file, any other writer, which is not within that same transaction, is the open is failed essentially.
Okay, and the other question is like, does this transaction apply at the volume level? Like, let's say I create a file, and then I about the transaction, the created file is gone, or at what point? I mean, what is the scope of this transaction, basically? Is it for the existing file, or it is for everything?
Okay, so it's for everything, and the scope is pretty global. It's beyond the volume. Like in
It's
some of the
entire.
examples, in some of the slides we showed you, the transaction can spread to other machines even.
Okay, thanks.
I have a question. If we have a network share that's supported by, like, say, a Linux server through Samba, what's going to happen if we have a transaction that originates from the Windows client?
Okay. That's a very good question. As you can imagine, when we are changing the protocol, SMB protocol, there are protocol changes required here. So, yeah. Okay.
Will you just fail the attempt to access the non-transactionally aware resources?
Currently, we are not doing anything like that. We will simply send it out. We would simply send it out over the wire, and we expect the backend to support that. If they don't support that, then just like any other protocol change, the results are unpredictable. And I really don't know enough about Samba to know what will happen. Sorry, you have to run it and see.
But there won't be a mode where you can say, make this attempt fail because that other part doesn't.
There is no way for us to find out whether it supports it or not to begin with. Right. Yeah, if it's a legacy one, then then that might fail. So they might actually be, this is something that's still working through, as you can imagine, because I'm still kind of trying to see how this will actually work. This is something that is still kind of in process. So exactly what the behavior is going to be is not determined yet. So, but there are protocol changes here, is all I can say. Okay.
Question. Do we have any changes to mini filter architecture to kind of so that this will work?
So yes, the filter manager has evolved.
Okay.
The filter manager supports transactional NTFS, and so if you have been, you have probably kept up with the filter manager over the past year. If you attend the driver DevCon, the upcoming driver DevCon,
Yes.
We will talk about the filter manager interfaces that are being exposed right now.
Okay.
And what you can be sure of is that if you have a mini filter that you develop, that mini filter can be very easily augmented to work with transactional NTFS going forward in the future. And that will be a lot easier than trying to take your legacy filter driver and then trying to retrofit it to the world of transactional NTFS.
So that is not in the, it has to come in the IFS kit, right? All those information.
So the distribution mechanism also, we'll talk about that later. I would highly encourage you to attend the driver DevCon and the IFS interoperability plugfest portion of that.
Okay.
And we'll talk a little bit more about that.
Yeah, I'm attending that.
So that'd be great.
Thank
Love
you.
to see that.
Your distributed on your slide with distributed transaction, there was no DTC. So does it mean that DTC gone if there is a kernel transaction manager? There is no DTC.
Yes.
That was a generic slide.
Yeah.
Clearly, I mean that slide. If you saw, there were two pieces called CRMs. So depending on the protocols, if you're using the OLE-TX protocol to do the marshalling, and you can actually specify that if you saw in yesterday's talk, Don Box and Jim Johnson. So depending on the protocol that you pick, the pieces could be actually DTC services on both. So those CRM boxes could actually be renamed DTC services.
Okay.
So or they could be something else.
So if I have two Longhorn servers,
right,
then DTC will not be involved because you will use like new protocol.
If you use a new protocol, then it may not be the old DTC that you know in terms of CRM pieces. But if you use OLE-TX, then sure, it'll be there.
Oh, okay.
So yeah, it's there.
Okay. So I guess that's it. Thank you all very much for coming and attending this talk. Thank you.
Been a good audience. Thanks.